Have you ever built a code editor or compiler that checks for matching brackets? That's the heart of LeetCode's valid parentheses, a pattern mastery 100 classic and one of the most asked interview questions at Google and Amazon. Over 25% of candidates trip on subtle edge cases. Let's make sure you're ready for any bracket puzzle. Let's tackle this using the basic method, so you'll be able to break down, structure, and explain your logic fluently. Given a string containing just comma, determine if the input is valid. A string is valid if open brackets are closed by the same type. Open brackets are closed in the correct order. For example, are valid, while, are not. Edge cases, empty strings, single characters, or mismatched brackets. Imagine you're building an online IDE that needs to instantly alert the user if their code's brackets are balanced before they hit compile. You want this logic to be fast and foolproof? A brute force solution might repeatedly search and remove pairs, but that's inefficient and hard to scale. Optimal approach: use a stack. Every time you see an opening bracket, push it onto the stack. For every closing bracket, check if the top of the stack matches. If it does, pop. If not, or if the stack is empty, it's invalid. Time complexity: O(n), space complexity: O(n), in the worst case, for all opens. Here's the plan. Initialize an empty stack. Create a mapping of closing to opening brackets for quick checks. Loop through each character. If it's an opening bracket, push it onto the stack. If it's a closing bracket, check if the stack's top matches the corresponding opening. If not, return false. Pop if it matches. After processing, if the stack is empty, return true. Otherwise, return false. Let's narrate the logic. We begin our solution class, the place where our bracket validation logic will live. This method, isValid, takes a string s made of brackets and returns true if the brackets are properly opened and closed in the correct order. Otherwise, it returns false. We create a stack to help track opening brackets. A stack works perfectly here because it follows last in, first out. The most recent opening bracket must be matched by the next closing bracket. We define a map called pairs to store each closing bracket and its matching opening bracket. This helps us quickly verify whether a closing bracket is paired correctly. This tells us the closing bracket should match the opening bracket, and here we say must match. Likewise, must match. This closes our bracket pair map definition. We loop through every character ch in the string s. Each character will be either an opening bracket or a closing bracket. This comment explains the logic we're about to apply. Opening brackets get pushed onto the stack. We check if the character is one of the opening brackets. How? By checking if it appears in the values of the pairs map, since all values are opening brackets. If it is an opening bracket, we push it onto the stack. This records that we must later see a matching closing bracket for it. Otherwise, the character must be a closing bracket, since those are the only types in the string. Now we need to verify whether this closing bracket matches the most recent opening bracket. Two conditions make this string invalid immediately. Stack dot is empty. There's a closing bracket, but no opening bracket to match it. For example, stack.peak equals pairs.getch, the top of the stack, most recent opening bracket, does not match the required opening bracket for this closing one. Example, the stack's top is, but the current character is, mismatched pair. If either happens, invalid parentheses. So we return false right away because the string cannot be valid. This closes the mismatch checking if block. If the brackets match correctly, we remove the opening bracket from the stack because we've now successfully paired it with a closing bracket. This closes the else block for handling closing brackets. This finishes the loop over all characters in the string. Finally, we return whether the stack is empty. If it's empty, every opening bracket had a matching closing bracket, the string is valid. If it's not empty, some opening brackets were never closed, invalid. This final check ensures completeness. This closes the isValid method. And this closes the entire solution class. Time complexity note: each character is pushed or popped at most once, so the total time complexity is O(n). The space complexity is also O(n) because, in the worst case, the stack may store all opening brackets. And that's how this algorithm works. It first sets up a mapping of matching bracket pairs and uses a stack to track open brackets, then checks closing brackets against the last open one to ensure proper order. Efficient, simple, and elegant. Let's test our function with this simple, clean input string. The string contains just one pair of parentheses, and our goal is to check whether the parentheses are valid, meaning they open and close in the correct order. When we scan the string, we see, push it onto the stack. Then we see, it matches the last opening parenthesis, so we pop it. At the end, the stack is empty, which means every opening bracket has a proper closing counterpart. And the program returns true, exactly matching the expected result. So, our implementation is correct. The algorithm properly validates the parentheses sequence, simple, efficient, and passing the test case. We begin by defining the solution class, which will contain our method for checking if a string of brackets is valid. This method receives a string s and returns true if all brackets in it are properly opened and closed in the correct order, and false otherwise. A quick comment saying we're about to build a mapping from closing brackets to their matching opening brackets. We create a character array map large enough to index by ASCII codes. This lets us map a closing bracket directly to the opening bracket it expects. We define the mapping for its matching opening bracket is, for its matching opening bracket is, and for the matching opening bracket is. We initialize a stack that will track the opening brackets as we encounter them. Think of it like putting brackets on a pile. Every time we see an opening one, we push it. When we see a closing one, we pop and check if it matches. We now loop through each character in the string. This loop runs in on time since we scan the string only once. We check if the current character is an opening bracket. If it is, we push it onto the stack. This means we've started a bracket that needs to be closed later. We skip the rest of the loop for this character since we're done handling it. Closing the opening bracket block. If we encounter a closing bracket but the stack is empty, that means there is no matching opening bracket. This immediately makes the string invalid. Here we pop the most recent opening bracket from the stack, and then check if it matches the expected opening bracket for this closing one. If it doesn't match, for example, we see, but the top of the stack was, then the string is invalid. Closing our loop through the characters. If the string is valid, the stack should be completely empty at the end, meaning every opening bracket found a matching closing bracket. If the stack still has leftovers, then some brackets never got closed. Closing the isValid method. And finally, closing the class. And that's how this algorithm works. It first creates a map for matching brackets, then uses a stack to ensure every opening bracket is closed in the correct order. Efficient, simple, and elegant. Let's test our function using this input, the string. This string represents a short sequence of brackets where we want to check if every opening bracket has a matching closing bracket of the same type, in the correct order. Here's why the solution works. Our algorithm uses a stack to track opening brackets. We read the first character it's an opening bracket, so we push it onto the stack. Next, we see comma this is a closing bracket, so we look at the top of the stack to see if it matches. The top of the stack is comma but does not match comma, they're different types of brackets. Because of this mismatch, the sequence is not valid. And that's exactly what our program outputs, false. This matches the expected result and confirms that the algorithm correctly rejects mismatched bracket pairs. So, our implementation is correct. The algorithm successfully identifies that this bracket sequence is invalid, efficient, accurate, and reliable. The takeaway? When you see problems about order, pairing, or nested structures, think Stack. It's one of the most powerful tools for building logic that mirrors real-world compilers, editors, and syntax checkers. Alright, let's wrap it up. The valid parentheses problem is a simple-looking but classic test of logic and stack mastery, one that shows up constantly in interviews because it reveals how cleanly you can reason about structure and order. We started with the core goal. Check if every opening bracket in a string has a matching closing bracket of the same type, and in the correct order. It's all about maintaining balance and proper nesting. We compared approaches and saw why repeatedly removing pairs or scanning back and forth is inefficient. The optimal way is to use a stack, a perfect fit for problems that follow a last opened, first closed pattern. Our logical plan was clear. Use a stack to track opening brackets, map each closing bracket to its match, and check as we go. If something doesn't match or the stack empties too early, it's invalid. If we finish with an empty stack, it's valid. We implemented the logic step by step and ran it successfully on LeetCode. No errors, smooth execution. Every test case passed perfectly, confirming that our stack-based approach handles all types of bracket combinations, including tricky edge cases.